Kelly Hill. I'm going to be your moderator today. I'm the editor for Test and Measurement at RCR Wireless News. I've been covering us for quite a few years now. And I'm joined today in our panel excuse me, by Ifti Rahman from Verizon Wireless Device Test, DMTS. Yes. And Dr. Abhishek Singh from Ethertronics, Senior Antenna Engineer. We also have Joy Laskar, CTO of Maja Systems. And we'll be joined momentarily by Emil Ulbrich, who you saw speak this morning from Prime Live. So gentlemen, we're going to start off here. And given that we're in a pre-5G standards situation, however much AT&T marketing might wish otherwise, I want to start out and ask each of you to give a little bit of an introduction to yourself, your perspective, and also tell us, what makes something 5G to you at this point in development. Joy, do you want to start?
Sure. Thank you. Thanks for having me on the panel. So I'll just give a little bit of background of what we do. We're Maja Systems. We're a startup in Silicon Valley. We focus on layer 1 CMOS-based solutions at millimeter wave. We've been at this for several years. We just started announcing a product last year. So I also brought a couple of props to pass around. We get to visit back, but this gives you an idea of what we do. So this is a single chip millimeter wave CMOS radio. We have solutions at 60 and 80 gigahertz and in development at other frequencies. But to give you an idea, this includes both a modulation engine, ADC DAC, as well as a full transceiver. And we also embed about 1,000 bits of digital control so that we can do things like pass-fail the solution digitally. So we think this is kind of a precursor to some of the architectures that people are working on to support 5G. We also co-design that into antenna systems. So some of the discussions in terms of OTA versus contact, etc. So you can see the way this works is just bits in, digital in, you take over the air, high level of integration, or since we're a small company, we don't build lots of modem technology, you can bypass modulation and use external modem modulation. So that's kind of what we do and what we kind of ship into markets right now. Pass this around.
Put your hands on actual millimeter wave technology.
Yes, I'm Ifti Rahman. I'm with Verizon. I guess everybody knows what Verizon is. But my particular, I work for a group called Device Technology. So our primary thing is to write the requirements for the devices and also to figure out how to test them. Obviously, when I say figure out, this is all at a relatively high level, so we don't really do requirements for design per se. It's relatively high level, but it's pretty still significantly detailed, I think, that we do. So obviously I know there are design challenges, but we don't get into it. We only worry about how to be able to write requirements so that we can, it's verifiable in a sense. So, and of course, requirements is pretty broad. There are different kinds of requirements. But, and then the challenge is more from the testing side, because we really have to also kind of write requirements for our test equipment vendors. And RNS actually have been working with them in different areas in the past, and I think they know that we did build something quite, a lot of things novel to test, which has probably never existed before. So that's, and my current focus is actually 5G. So I've been working on it for about a year and a half or so. Or trying to work in it, let me put it that way. And we are actually, there is something existing. If you go, it's something called 5G Technical Forum, Verizon 5G Technical Forum. It's, of course, everything that we did is not published. But a lot of it is published, so you can see that. And so we are actually working on something naturally to build to the 3GPP standard based on those 5G Technical Forum work that has been done in partnership with our various vendors, chipset, and infrastructure.
Abhishek Singh, work for Ethertronics based in San Diego, California. Ethertronics is a leading antenna system manufacturer and vendor for a lot of platforms, mainly including cell phones, laptops, and other consumer electronic products. We also design embedded antennas for a bunch of other applications, including IoT. And the company has been around since 2000, so we have been involved in the antenna design aspect for smartphones, right from 2G to 3G, LTE, and now we are seeing more and more traction from our end customers as they're starting to investigate, and as 4G kind of evolves into 5G. We want to understand the industry requirements, and obviously the antenna here, as you've seen in the discussion from the presenters so far, is going to play a very important role in 5G because especially when it comes to millimeter wave in this case would be the higher frequencies, the 6 GHz plus frequencies of 28, 38, 60 GHz or even higher, where the propagation component plays a very important role. You have path loss, you have shadowing effects, and you have so much atmospheric attenuation that takes place at higher frequencies. You need an antenna structure that has a lot of gain. So moving towards antenna arrays, that is the logical next step. But I'm also going to be presenting later this afternoon, where I go over some of the challenges when it comes to designing antenna arrays. There is feed networks, there are losses that need to be taken into account. And obviously, as we looked at earlier, there is an effect whenever you make something high gain, you deal with a narrowing beamwidth. So what are the different things that can be done from the antenna side to assist with the whole problem here? And also to bring in a perspective of making something which is not just theoretical, something that can actually be mass produced, because that has been our area of expertise, in a low cost and a cost effective manner, and how to kind of integrate with the whole system.
Great. I do want to step back and ask each of you at this point, what makes something 5G to you? Obviously, AT&T is trying to bring the perspective of speed in, whether it's speed, you know, whether it leverages millimeter wave or not, you know, and maybe to what extent it's software defined. I don't know. Joy, what about you?
Well, sure. I'll just give you my opinion. So I think you know, data rate throughput, multi-gigabit over the air, actual net throughput, like that little thing that's going around, that's 4 gigabit over the air. So you know, certainly that followed wireline type throughput or Ethernet type roadmap. Delay, as we've already seen, is extremely important, both at the layer 1 and also end to end. But I'd also throw in, you know, swap size wave power, right? Meaning, you know, the first millimeter wave link was demonstrated in 1895. So, you know, the issue, a lot of the issue is to make these things production worthy at a cost structure that can be available to everyone. So there's a lot of things that we have to come into that. But I think for 5G, from my perspective, it needs to be somewhat revolutionary, which seems much higher throughputs, much lower delay, and ubiquitous.
Yeah, so I mean, actually, I'm not, obviously 5G promises, I mean, the big thing is probably the range is much higher, but I'm not sure whether delay, it depends upon, you know, what's over the air, you know, what's the difference between 1 millisecond versus 0.1 microsecond, probably doesn't make any difference. But end-to-end, yes, you know, I mean, I probably think that that's the more significant portion. Now, so I think it's really also, even though, you know, we have carrier aggregation before, it's not new, but I think still the amount of bandwidth that is expected to be used is probably to me the significant portion of 5G.
Yeah, 5G, yeah, I'll go with the standard expectation. When most people think 5G, you're talking about gigabit speed, higher gigabit type of speed. And low latency, yes. One of the things that comes to mind also at 5G is if you're doing millimeter wave, this is something high frequency, higher antenna gain type of application that can get you there. Even if it is sub gigahertz, you think in terms of massive MIMO type of application, where you need to significantly grow the number of elements to kind of achieve the bandwidth requirements that come into play at 5G. So yeah, in essence, that is what comes to mind when we think about 5G.
So we have chipset, antenna, and device. And so I'm going to ask each of you, what do you see as the primary challenges in the area, either of design, if it's relevant, or test, if depending on which is more relevant for you?
Sure. So for us at Maja, I mean, the historical perspective again, right? You've had millimeter wave links for a while. The CapEx and OpEx really hasn't been sustainable, even at layer one. So if you just kind of look at the type of solutions that have been built, even until fairly recently, something like 80 to 90% of the cost structure, for example, the layer one component and the layer one components into the link are assembly, test, and antenna, or how you feed the antenna. So it seems to us what we do is basically try to collapse the CapEx from highly integrated solution, but that includes test, or in effect has some form of self-test, so that you can collapse that structure. And then for OpEx, as we've already sort of seen earlier in the day, when you deploy these links, either auto-aligning or beam steering. So to us, at the layer one, is embedding as much of that functionality that impacts test, and that also impacts the link operation of the line.
So cost and functionality.
Cost and functionality.
Okay.
Yeah, okay, so mine actually is relatively maybe simpler, but my primary concern probably would be, have I captured the environment? For example, you have a link budget, but that's not really dynamic. Of course, we do need the link budget to spec the device or device form. But at the end of the day, there is a lot of dynamic factors. Do we have a good model? Because even though I'm on the device side, I still have to emulate the network in order to test, make sure that the device is undergoing the right type of test. So to me, that probably is the key element. And of course, the beamforming is a must, as Dr. Abhishek has mentioned. That's really must in order to get the gain. And how do you test? So we have different kind of tests here. We do control tests, thanks to people like Rudy Schwartz, and then we also do on the field tests, which is not really controlled. So want to in a control test, obviously, since you're control, you need to control the environment. So I want to make sure that I'm testing for the right environment.
And when you approach test in that sense, how do you think about approaching test plans? Are you basically just coming up with, whatever you think is the most efficient and see what sticks, or see what really, what data ends up being the most relevant?
Right. So we want we obviously want to test. So when we write the specs again, we have to also worry about. We have to think about the different environments, right? Because we want to say that, because the context, right? It's a scenario, it's really a scenario, right? So it's an environmental scenario, so you want to spec it and say that for that, this is the performance, right? But I can't say, a whole range, right? You can't test maybe a whole range, let's say. So that's really the most stable way to do it. So you want to, within the range, you want to cover the extremes and something in the middle, and you want to be able to test it. So in order to come up with a number, you must know the environment is also. So based on that, and there's also some dynamic effect that you want to come into play, right? Because it's not static. Propagation isn't static. So.
Even if it's fixed.
Yeah, that's right. Even if it's fixed, that's a good point.
Okay.
It's always dynamic, yeah.
Abhishek?
Yeah, so two aspects of the challenges that come into play here. The first being design. but kind of equally important, if not more important, is validation and test. Because a design can be excellent, but it is only as good as what the test results reveal. So the design challenges, as Joy already mentioned, what we are seeing kind of the logical way to go is to do smart antenna arrays or adaptive antenna arrays. But even in the more traditional sense, if I take an example of 802.11ac, which employs digital beamforming, which is a smart antenna system which uses phase information, and instead of just locking, for example, a 4x4 system, instead of just locking the system into some predefined array patterns or beam patterns, they are adaptive in nature, wherein there is an feedback loop, closed loop with the baseband post processor, and it can use metrics like signal to inference noise ratio, RSSI, etc. And it can make a decision on how to beamform and change the shape of the beam in real time. One of the challenges with these type of designs is right now for Wi-Fi, for example, this is done by introducing a front-end module with a power amplifier, low noise amplifier on each part for each of the antenna elements. Now, when you start thinking about these arrays where you'll have 64, 256, or even more elements, the cost, the actual feasibility, factors like heat dissipation, cause there are several things that need to be taken into account of how you would employ some type of traditional beamforming here on these designs. Also means there has been work that has been done on looking at hybrid approaches, wherein you could have one front-end module controlling 2, 4, or multiple antennas at the same time. But the kind of design challenges will be how to synchronize the logic to use something like that. And following all of this, just from the layer 1, just from the antenna and FEM test perspective, there are two things. One is how do you validate something in the lab, which is kind of your basic consideration for the design and test engineers. And the second thing which Ifti mentioned is, for example, for LTE, there are well-defined field trials that the carriers have in place, how you test things close to the cell site, edge of cell, mid cell, etc. For this type of scenario for 5G, what would be your typical field trial scenarios? How do you test it? How do you validate it?
So we had a little bit of discussion, I think, this morning about channel models and about this sort of a state of industry knowledge. And then Wilhelm had his session downstairs about channel modeling. Where do you think we are in terms of industry state of information? How well do we know the spectrum and can anticipate behavior at this point? What from your perspective needs to be done to get a better sense of what's going on at the test?
So from a channel model, I think, as you mentioned earlier today, I think we're still very early. And also, certainly millimeter wave, there's quite a few different bands that are being considered. So those are very different channels. And the reality is, like, for example, a revenue-generating millimeter wave mesh network doesn't kind of exist yet. So there's lots and lots of, I think we're still very early in that.
Right, so let me make a pitch for the 5G forum, by the way. This is a channel model, but I agree, it's nothing to complicate. And I think recently I got an email from, without naming names, complaining that the 3GPP is not modeling it right. I don't know if it's in there. But anyway, yeah, I think it's probably still too early to say that we have a complete model which covers all environments, all the relevant environments.
So environments meaning indoor, outdoor, urban versus suburban, as opposed to different spectrum bands.
Yes, yes. I mean, of course, spectrum band also matter.
Also, but in addition, let's.
Yeah, just wanted to talk about the spectrum plans. For example, one type of visualization, 28 gig, 39 gig, 60 gig. Even just going from 28 to 39, or taking the example of 28 gig to 60 gig, the propagation environment is significantly different. The wavelength is significantly smaller as we go higher in frequency. The path loss and the reflections are extremely different for these two scenarios. So till we that would be at least a first order of trying to come up with an accurate channel model once we know kind of the frequency spectrum that we're dealing with. What we saw this morning in the workshop also was a good demonstration of one approach to model the channel, but we're still doing this based on a lot of assumptions, and there are several complexities to the channel model that probably in the initial setup can be taken into account. So based on that, yeah, we need to move forward, but once we have at least the frequency spectrum definition, we can look at ways and means how to characterize the different effects of multipath reflection. And then obviously there are ways, ray tracing is commonly used. There is also the debate between how accurately at 28 gigahertz does a ray tracing simulation line up with actual field charts. And that type of data set needs to be collected to come to an agreement.
To figure out how much we don't know at this point.
What is the error margin?
Yeah, whatever model you come up with, you need to refine it based on data which you
Yes.
Great. Let's talk a little bit about 5G in the manufacturing environment. Joy, I think particularly for you this has some relevance in terms of, you talked about cost and ensuring functionality. You're talking about some very tiny, lots and lots of very, very tiny and complex components. What implications does that have for, for repeatability and scale in the manufacturing environment?
Yeah, sure. I used to have a lot more hair, for sure. I think at volume, if you will, millimeter wave, it'll be, by definition, it'll be very different than how we historically have done things, right? So, in a test environment, just to give you an idea, right, at millimeter wave, a V-band coaxial connector is somewhere between $500 and $1,000. That's just one coax adapter, right? So you can imagine what that means if you have an interface that has maybe 10, 15, 20 of those on there, right? So there's lots of implications, but I think what's pretty clear, you can see that at the layer one sort of solution that folks are developing is, and it was mentioned, I think, in one of the talks earlier today as well, is you're going to see probably as much functionality embedded in the radio as possible, at an IC level. The other thing that's a little bit different at these higher frequencies is, you typically, the radio is more intimately physically connected in proximity and distance to the antenna, because no one wants to route lots and lots of waveguide or expensive coaxial connectors. So that also has implications. So basically your antenna and your IC will be intimately connected in some form. And working, maybe a little counterintuitively, what we do, for example, right now is we spend a lot of time with the type of composite production phase. And what we end up doing is generating what we call correlation vectors. So we correlate the millimeter wave characteristics to digital inputs that we control. And we do that over thousands and thousands of elements at a wafer level. And then for us at least, and this probably is true in general as these things scale, at the manufacturing environment, at the wafer level, we want to be able to do basically pass-fail tests effectively digitally with those correlation vectors. So then when we get to folks like Ifti, et cetera, there it's much more of what we view as a link analysis where we've already given a pass-fail on not only the IC or the radio, but also at least that first layer of the antenna, right? So at that point, then it's much more of a compliance test, a spectral compliance test, et cetera, but it sort of simplifies the stages. So, and the reason is otherwise, it's extremely difficult. Again, historically, at lower frequencies, the cost structure is about a third of the chip, actual manufacturing of the chip, a third the assembly, and a third the test. Historically, at millimeter wave, it's 90% of the cost structure has nothing to do with the chip manufacturing, right? It's the assembly and the test. So that has to be collapsed.
Abhishek,
I'm
I'm
gonna
going
do
to
it.
jump to you. Yeah, I'm going to jump to you. But I do want to ask you though, what you're seeing obviously you're probably working on prototypes at this point.
Yeah, we have prototypes, and obviously we have ongoing discussions on, but it's too early to talk about. We only look at it from the viewpoint of cost, right? So, rather than how do you bring that cost down and all that. We just want obviously something cheap, but we don't worry about how to bring the cost down.
But do you worry about things like, obviously at some point you do have to worry about things like, consistency in behavior.
Of course,
Yeah.
Stability.
Stability,
Yeah.
exactly.
But that's the kind of, you look at the, I think Joy mentioned, you look at the actually the finished product, right? The closest we get to not a complete product might be a module, but that's still quite finished also.
Abhishek, you want to comment on mass production from the antenna
Yes,
point of view?
actually, it's really interesting the comment that Joy made about the connector cost V-band. One thing, as we move further, the implementation can be fixed where you have a base station talking to a receiver at a consumer's home. At some point it will, you are also looking at obviously fixed mobile scenario wherein your smartphone actually has this type of antenna array embedded, and there have been some initial work and even published work done on this in the smartphones. Just the cost model in a smartphone, typical solution, I will not give exact numbers, but it's in the very, very low dollar range when you're typically designing a solution. So obviously, using connectors and stuff like that is not going to be a very feasible option. One thing that Joy also mentioned, one of the main reason of kind of integrating the antenna structure closer with kind of the ICs at the front end is from cost. The other reason is also the losses, the insertion loss that comes into play once you have these components sitting further away from the feed of the antenna can be huge. These can be few to several dB based on how they're designed. So these are the factors that come into play when you look at the cost of the solution. The other thing is for manufacturing. For typical applications right now, the substrate material that is used is for low cost, can be easily sourced from pretty much anywhere in the world. The problem at higher frequencies is the same FR4 material becomes extremely lossy. In addition to that, even the heat dissipation characteristics kind of suffer. So what we have to go to is kind of more expensive, low loss dielectric materials, which kind of bring up the cost. Now, in addition to that, we need to look at other things like etching tolerances, because everything, kind of the sample that went around, you can actually see it's a big array of antennas in an extremely small form factor. There is an etching tolerance, which is the line width and how the patterns are. They have to be carefully controlled. All of these are cost orders, adders to the whole equation. So from our side, we are already looking at ways how something like this can be manufactured in a cheaper manner, something that can be taken to mass production.
Yeah, exactly. In fact, just as an example, what we do, like in that array that you see there, to Abhishek's point, is what we do is on the silicon or on the radio, we actually have tolerances that are correct for within a band, a range of losses, et cetera, that we expect from a low tolerance manufacturing environment. So if that makes sense. So in other words, the PCB flow for the antenna is sort of a very wide, sloppy design window. And then on the radio, we automatically tune and adjust. Right? So otherwise, we would never be able to make that work. Right? So things like that are embedded, I think, in having to occur.
So I want to talk about general test approach in terms of cable or connected versus OTA. I think a lot of folks have mentioned OTA kind of tangentially. I'm sure you're going to get to it in your presentation. But perspective on on how that sort of approach is going to change in 5G.
Well, I'll make maybe what these folks will know more, but the other thing that's interesting is, at Core 5G or these type of solution sets, right, especially knowing the way the test equipment environment changes. So just, if you just take a step back from there, for example, you'll have the spectrum analysis, the network analysis, but you also carry the type of test equipment you would use for wireline types of things, right? So literally in a lot of these labs, right, you've got spectrum analyzers, network analyzers, bit array machines, right? High-speed, real-time scopes, all together because you're capturing in real time the frequency waveform and in effect the time domain waveform. And you're also, we already see requirements, because a lot of our things go into more embedded solutions, right? So we already see requirements from customers where they want the solution either at chip to module to link to be characterized like a wireline. So we actually have to provide bit error rate and jitter information on a wireless link, which is kind of unusual, right? So I suspect that that type of need is going to go into some of these use cases.
Thoughts on OTA versus connected? Do you focus on a particular?
We actually do both, but the thing is here that we have an additional thing called beamforming, which existed before, but it's there in MTE, to the best of my knowledge, but you're seeing it for the first time here in 5G, so obviously there has to be a lot of radiated testing also. We need both. So because at the end of the day, we actually look at throughput essentially, right? We don't look at, we don't need to look at spectrum analysis per se, when we have it just for the fun of it. It probably comes a bit quick, but we are interested more in the data throughput level. So even with OTA, we see what is the data throughput achieved. So it's more of a macro look.
And performance.
Yes, so whether we do conductive or radiated, still looking at a more macro level.
Actually, I agree with both of them. There needs to be a good way to measure conducted before you kind of move to OTA. The thing with OTA here is there are too many scenarios that come into play, and how do you characterize it? And typically, for any initial design, the first order is always verification in the lab before you go to the field. In the field, what can be done is initial sounding measurements to kind of get an idea of what would be the test scenario, what would be the use case. Then you kind of need to go back to the lab and try to simulate those scenarios before you actually do any type of OTA or field test. Beamforming, for example, validation is done, like for example, at Wi-Fi frequencies, it is done both the chambers which are able to characterize beamforming matrix. So these are small anechoic chambers where you can do rate versus range measurements to do a characterization. You can also do real-world testing in test houses or different office environments, and you can characterize it by placing a DUT at several locations with several times. Becomes a bit easier when you're doing at that frequency. But it is always easier to do the first order in kind of conducted or a lab environment. So that would be definitely a priority in terms of development.
Now, I think some of your compatriots from Verizon today put up kind of a wish list of, of things that they would like to see, or areas that they felt needed more support in terms of the overall 5G ecosystem. I wanted to wrap up by asking each of you, if you had one piece of test equipment or test process that you could put on your wish list to really advance what you're doing in the 5G arena, what would it be?
We would, we've actually mentioned this already short. So we love their spectrum analyzer because it's a single connection, snapshot, very wide band. But I can imagine a capability where we have basically spectrum analysis and in effect, bit-array testing capability in one box. So that way you're looking at spectrum, eye diagram, et cetera, et cetera. And it's pretty comprehensive sort of. And for the other comment I would make on there's a lot of different ways to look at the quality of a link, especially these frequencies and variations. What we find is, just for example, a simple test like sending an uncompressed video signal with no signal processing on the link. And for example, to lock to a screen, like a TV screen, you have to have better than 10 minus 9 bit array and better than 0.1 UI jitter. So as we see these things evolve, those are the kind of things that it's going to be contrasted against, right? Meaning that if you were competitive technology, which will be a wired technology in many cases, that's what people are going to be looking at.
Well, yeah, we haven't thought about it. We're concerned more about the requirements at this stage. We're not quite even the verifiability.
What would make your life easier?
Well, I said I would like to see between the beamforming, how do I test it? So in a closed environment.
So some kind of a chamber.
I want it to be chamber.
A huge chamber for millimeter wave.
Yes, to the smallest possible. Right? Probably that would be, if you want me to say, you can't have several and number one, then probably that would be interesting. But I'm not at this stage, I'm not sure I'll do this thinking about it. We have not really thought about what should we ask our test equipment vendors to build to. That would be something that would be interesting. Apart from how do you have to create an environment in a control setting.
Anechoic or reverberation?
Don't know.
Yeah, actually, Joy and Ifti basically covered both the points. So the first one is obviously something on a single test bench, whether it's one spectrum analyzer with the second device or everything integrated into one device. So it's kind of a dream wish list to test something like this. The second part is also you need for digital beamforming or even to look at the antenna functionality instead of just looking at EM simulations, which are pretty accurate for simulating arrays and radians. But to look at overall system performance, for example, for 3G and 4G system, the carriers have total radiated power specs, TRP specs, which can be validated in an anechoic chamber with a very quick test. Kind of moving towards something like that, which could be tested in a chamber to kind of give not just the antenna characteristics, but antenna plus the system characteristics in a more automated manner. That would be kind of the best way to.
The end, you kind of
That's a
put it
good
all
point,
together.
automated.
Yes, automated, fast and cheap, right? All right, well, Rody, you guys can take notes on that wish list. So thank you so much, everyone. Thank you to our panelists, and we'll move on with the rest of